Okay, let's unpack this. Imagine a field of science, right? Bubbling with these incredible ideas, discoveries happening all over the place, brilliant minds. But like, no central map, no anchor.
Yeah, like a whole bunch of amazing research, but no shared language,
Yeah.
almost disconnected.
Exactly. Disconnected. Then, suddenly, this one text drops. And it just pulls everything together. It shapes a whole generation, totally transforms the landscape. That's the story we're diving into today.
We're looking at the huge impact of the 2016 textbook, Deep Learning, by Ian Goodfellow, Yoshua Bengio, and Aaron Courville.
And it wasn't just, another textbook. People started calling it the Deep Learning Bible.
They really did. It became the guide. It unified decades, literally decades of neural network research, introduced deep architectures, optimization applications, all into this burgeoning field that was, frankly, crying out for it.
It gave it a coherent framework, right? Made it accessible.
What's so fascinating, I think, is how this text really marked the coming of age for deep learning.
Coming of age, yeah.
It took it from being this sort of niche, maybe even slightly dismissed area of AI research, and bang, suddenly it's the central paradigm, the dominant force we see today.
So we'll get into the core concepts it distilled, right? The architectures it laid out.
And why that coherent framework was just so crucial for the explosion of growth we've seen since. It really makes you wonder, how does one single book become that pivotal in a field moving this fast?
It's a great question.
It gave people a common language, a shared understanding. That was huge.
So this deep dive, it's definitely for you if you're, say, prepping for a meeting, trying to get up to speed on AI fundamentals, or maybe you're just, super curious about what actually makes today's intelligent systems tick.
From your phone to the big language models.
Exactly. Expect some aha moments, I think, and maybe some surprising history, too. Okay, so to really get why this Deep Learning Bible was such a big deal, we kind of have to go back, way back.
Yeah, you need the context. The landscape before 2016.
Because there were decades of work, right? Moments of huge excitement then. Boom. AI winters, skepticism. It wasn't a smooth ride.
Not at all. A real roller coaster.
Let's start at the very beginning, the absolute earliest ideas, like the first glimmers of thinking about an artificial brain.
Right. You have to go back to 1943, McCulloch and Pitts. Warren McCulloch, a neurophysiologist, and Walter Pitts, this incredibly bright young mathematician.
43. Wow. What did they propose?
Their work was just foundational. They introduced the very first sort of abstract mathematical models of artificial neurons. It wasn't about building hardware yet. Not really.
Just the concept.
Exactly. The concept that computation could be inspired by the brain. They showed on paper that you could simplify neurons down to these binary units. They either fire output 1 or don't fire output 0.
Based on input signals?
Yeah, based on whether the sum of their inputs crossed some threshold. It sounds simple now, maybe, but it was this massive leap. It showed you could theoretically model brain-like computation using simple logic.
Taking biology and making it computational. Abstracting it.
Totally. Revolutionary abstraction. Imagine trying to explain thought, and I say, well, what if we model just one tiny part mathematically? Huge.
Okay, so that sets the stage conceptually, but then came something more concrete, maybe more exciting, the perceptron.
Ah, yes, Frank Rosenblatt, 1962. Cornell psychologist. The perceptron felt much more like a practical step.
What was the big idea there? What made it groundbreaking?
It was a real early neural network because it had a learning rule. That was the key. It could actually learn.
Learn what, though?
It could learn to find a solution for what we call linearly separable datasets. And they could do it in a finite number of steps. This wasn't just theory, it was proven. The perceptron convergence theorem.
Linearly separable, like you can draw a straight line between two groups of things.
Exactly like that. Imagine plotting apples and oranges based on, say, redness and roundness.
Yeah.
If you can draw one single straight line to perfectly separate the apples from the oranges, that's linearly separable.
And the perceptron could find that line.
It could learn to find that line, yes. Yeah. By adjusting its connection strengths, its weights, it could learn from data how to classify things. It was incredibly inspiring. Got a ton of attention.
A machine that learns. Must have seemed like science fiction, but if it worked for those problems, why wasn't it just smooth sailing from there? Hashtag 1.2, the AI winter for neural networks and the rise of symbolic AI.
Well, yeah, about that smooth sailing. Despite that initial buzz, neural network research, pretty much, became virtually dormant by the late 50s, early 60s. It hit a wall.
An AI winter, specifically for neural nets.
Exactly. And a huge reason, maybe the reason, was this really influential critique by Marvin Minsky and Seymour Papert at MIT, Giants in the Field.
Their 1969 book, Perceptrons.
That's the one. Perceptrons, an introduction to computational geometry. They basically took the perceptron apart mathematically and showed its limits. And that book has a very, very long shadow.
So what was the killer limitation they found? What couldn't it do?
The big one was its inability to solve non-linearly separable problems. Problems where you can't draw that single straight line.
Ah, like the famous XOR problem.
Precisely. Exclusive
Oh.
OR. The classic example. Think of your apples and oranges again. What if the apples are top left and bottom right, and oranges are top right and bottom left?
Okay, yeah, no single straight line can separate those.
Nope. You need at least two lines, or a curve. Minsky and Papert proved, rigorously, that a single-layer perceptron mathematically could not solve XOR. It could only draw one line. Full stop.
Wow.
And that wasn't just some minor detail. It showed a fundamental limit. It basically told the world, look, this exciting perceptron thing, it's fundamentally limited. It was devastating. Funding dried up. Researchers left the field.
Just like that. One logic problem tanks a whole field. That's sobering. Shows the power of theoretical limits.
Absolutely. A hard lesson.
So with neural nets on ice, where did AI research pivot? What became the dominant approach?
Well, the focus shifted dramatically towards what's called serial processing of symbolic expressions, often called JOF-AI, good old-fashioned AI.
Symbolic AI. So less brain-inspired learning, more logic, rules.
Exactly. Mimicking human logic and symbol manipulation. Building systems that played chess, proved theorems, acted like experts by following explicitly programmed rules. Knowledge representation was key.
Trying to build programs that solved respectably difficult problems using rules.
Right. And this created, these intellectual battle lines. It became parallel processing versus serial processing, learning versus programming, emergence versus analytic description.
A real philosophical split.
Totally. And for decades, symbolic AI was king. It had successes, definitely, but sometimes the systems were a bit brittle, didn't handle ambiguity well.
So symbolic AI takes over, connectionism is out in the cold. But the story obviously didn't end there. Some people kept the faith, right? Kept working on neural nets behind the scenes.
Oh, absolutely. A determined few saw the limitations, not as a dead end, but, as a challenge, something to overcome.
And they started thinking beyond just one layer.
Precisely. Even during the AI winter, work continued quietly on multi-layer perceptrons, MLPs. The key innovation was adding hidden units, layers of neurons between the input and output.
Hidden layers, what did that change?
It changed everything, fundamentally. Those hidden layers allowed the network to learn intermediate representations. They could combine features in more complex ways, creating those nonlinear decision boundaries needed for problems like XOR.
So multiple lines working together effectively.
Kind of, yeah. Or learning more abstract features. It overcame the Minsky and Papert critique. It showed that adding depth could solve more complex problems. A massive conceptual hurdle cleared.
Okay, so MLPs could solve XOR. What about their theoretical power more broadly? Was there some guarantee they could learn anything?
Well, that led to the universal approximation theorem, a really powerful result.
Sounds important. What does it say?
Essentially, it says that an MLP with just one sufficiently large hidden layer can approximate any continuous function, given some mild conditions.
Any function. Wow. So, in theory, they could learn almost any relationship between inputs and outputs.
In theory, yes, immense representational power. But, and this is a huge but, that leads us straight to the deep learning book, Practicality Matters.
The catch.
The catch. For real-world, large-scale tasks, think high-res images, huge data sets, just making that single hidden layer bigger and bigger. It led to impractically large parameter counts and high computational costs.
Millions, billions of parameters, hard to train.
Exactly. Training became incredibly difficult. They were prone to overfitting, just memorizing the training data. They needed vast compute resources, often without even succeeding. So the theoretical power was there, but making it work in practice, that was the challenge.
And that practical challenge is really what the Deep Learning Bible started to address systematically.
Precisely. The field needed breakthroughs in architecture, in optimization, in regularization, ways to make these powerful models actually trainable and scalable. The stage was set.
Okay, so we got the history, early ideas, the perceptron excitement, the Minsky-Papert critique, the AI winter, the comeback with MLPs, but then this practicality problem. Huge networks, hard to train.
Right. Theoretical power, but practical hurdles.
Which brings us to the core of what the Deep Learning Bible did. It wasn't just writing things down. It was synthesizing, organizing, creating that coherent framework, making deep learning workable.
Yes. It laid out the unifying principles.
Let's dive into those, starting with the basic structure, the building blocks, deep architectures.
Okay, so if we connect this to the bigger picture, the book really clarifies how feed-forward networks are the general framework. They're for representing these nonlinear mappings, right? From inputs to outputs.
Inputs like images, text, outputs like classifications.
Exactly. And feed-forward just means the information flows one way, input, through the layers to the output. No loops back, straight through.
So where does the complexity come from? How do they learn nonlinear stuff?
The magic, or the math rather, comes from compositions of nonlinear functions, these things called activation functions. Each little neuron or unit applies one.
And that's what lets them model complex patterns.
Absolutely. Without those nonlinear activation functions, stacking layers wouldn't actually help. You just end up with another linear model, no matter how deep it was. The nonlinearity is critical.
I'm picturing data flowing through, getting transformed at each layer. Is that why the diagrams in the book are so important, the network diagram?
Totally. The book emphasizes that there's this one-to-one correspondence between the math, the function, and the diagram. It's not just pretty pictures, it's pedagogical.
It helps you visualize the flow, see how the transformations happen layer by layer.
Exactly. Demystifies it. Shows how you get from raw pixels, say, to identifying a cat.
Okay, so feed-forward networks are the general class, and MLPs, multi-layer perceptrons, are a key type within that. The book talks about their power, but also their limitations, right? Even with hidden layers.
Yeah, that's crucial. MLPs are powerful universal approximators, in theory. But the book points out their big weakness: inefficiency in parameter usage.
Inefficiency, meaning they need too many connections, too many weights.
Pretty much. And this inefficiency is a key reason why we needed more specialized architectures. Think about images again. Images have spatial structure, right? Pixels near each other matter more. Edges, textures,
Local pattern.
local patterns. But a standard MLP, a fully connected one, where every neuron connects to every other neuron in the next layer. It completely ignores that structure. It doesn't exploit it.
So it would treat a pixel in the top corner the same way it treats one in the middle. No sense of locality.
Exactly. It has to learn everything from scratch for every possible position. Imagine teaching it what a cat looks like in the top left, then again for the bottom right.
That sounds wildly inefficient. You'd need astronomical numbers of parameters.
You do. It's computationally expensive, needs tons of memory, hard to train, especially for high-res images. So the Deep Learning Bible, by clearly stating this limitation of MLPs, sets the stage perfectly for why architectures like convolutional neural networks, CNNs, were such a breakthrough.
Because CNNs are designed to exploit that spatial structure.
Precisely. They were the elegant solution to the MLP's inefficiency on spatial data.
Okay, so we have the architecture, but how do these giant networks actually learn? How do they adjust themselves? That's optimization, right?
It's optimization, the engine of learning.
And the book starts by talking about how to measure how wrong the network is, the error.
Yeah, it introduces the sum of squares error function. It's a pretty standard, intuitive way to quantify the difference between the network's prediction and the actual target value.
Like, if it predicts a house price is $300K, but it's really $320K, you square the $20K difference.
Exactly. Squaring it makes errors positive and penalizes big errors more. Simple and effective. And for basic linear models, this error function is nice and quadratic.
Quadratic, meaning easy to solve.
Relatively, yeah. You can often find an exact closed-form solution, like a direct formula to calculate the best weights. But for deep, nonlinear networks, forget it. No easy formula. The error landscape is way too complex.
So no magic formula. How do they find the best weights then? What's the main method?
The workhorse is gradient descent. It's the primary method. It's iterative.
Iterative, so step-by-step adjustments.
Right. Imagine you're blindfolded on a hilly landscape trying to find the lowest point. You'd feel the slope where you are, right?
Yeah.
And take a step downhill.
In the steepest direction downward.
Precisely. Gradient descent does that mathematically. It calculates the gradient which points uphill towards the steepest increase in error, and then takes a small step in the opposite direction, rolling down the error surface.
Okay, but here's where it gets really interesting, I think. The learning rate, the size of that step. The book stresses how critical that learning rate parameter is. Why is that so vital and so tricky?
Oh, it's the crucial hyperparameter. Eta dictates the step size. If it's too big, you leap right over the minimum. You might bounce around, even diverge completely. Error gets worse.
Like a ball bouncing wildly down a hill.
Exactly. But if it's too small, convergence is painfully slow. You take tiny, tiny steps. It could take forever, burn huge amounts of compute. It's clearly a very inefficient procedure.
The Goldilocks problem. Not too big, not too small. Just right.
Finding that just right is a huge part of practical deep learning. It can make or break training.
And what about getting stuck? Can the network think it's at the bottom when it's actually just in a small dip? The local minima problem?
Yes, that's a classic challenge. The error landscape isn't a smooth bowl. It's usually incredibly rugged, full of these local minima points that look like the bottom nearby, but aren't the global minimum, the true lowest point.
So simple gradient descent could just get trapped.
A purely deterministic version, one that always goes strictly downhill. Yes, it hits the first dip and stops. But the book points out something important. Most modern gradient descent is stochastic.
Stochastic, meaning it has some randomness.
Yeah, usually by using small batches of data, mini batches, to estimate the gradient, not the whole data set at once. This introduces noise. That noise, that randomness, means it has the possibility of escape from local minima.
Like a little jiggle that helps it hop out of shallow valleys.
Exactly. That stochasticity adds robustness, helps it find better solutions. It's a key reason why stochastic gradient descent, SGD, works so well in practice.
The book also talks about curvature making things inefficient. What does that mean?
Right. The curvature of E varies significantly with direction. Imagine a long, narrow valley. It's very steep across the valley, but almost flat along its length.
Okay.
Gradient descent might take huge steps bouncing back and forth across the steep direction, while making only tiny progress along the flat direction towards the actual minimum. It takes many small steps where it should be moving faster.
So it zigzags inefficiently.
Very inefficiently. This poor conditioning highlighted the need for more advanced optimizers methods like ADAM, RMS prop, that adapt the learning rate or account for curvature. Things the Deep Learning Bible explains in detail. Moving beyond basic SGD.
And the mechanism for actually calculating those gradients through all the layers, we have to mention backpropagation. Even if these specific snippets focus on the derivatives, it's the engine, right?
Absolutely essential. Backpropagation is the algorithm that makes training deep networks feasible. While the text talks about derivatives with respect to the output activations and recursive formulas, that is backprop.
Calculating how much each weight everywhere in the network contributes to the final error.
Yes, by efficiently propagating the error signal backwards from the output layer through all the hidden layers. The Deep Learning Bible details this, citing its use for training complex models like deep generative stochastic networks.
So without backprop's efficiency,
Deep learning as we know it wouldn't exist. Training networks with many layers would be computationally impossible. It's the algorithm that turned deep learning from theory into practice.
okay, architectures, optimization. But deep networks are beasts, right? Millions, billions of parameters. That complexity must be hard to manage. They can just memorize the training data, can't they? Overfitting.
Oh, absolutely. Overfitting is a huge risk. The model learns the training data perfectly, noise and all, but then fails miserably on new, unseen data. It hasn't learned the general pattern.
So how do you tame the beast? How does the Deep Learning Bible talk about keeping models stable and making them generalize?
That's where regularization comes in. Crucial techniques. One of the main ones is L2 regularization, sometimes called weight decay.
Weight decay. Sounds like it shrinks the weights.
That's exactly what it does effectively. It adds a penalty to the main error function, a penalty based on the squared size of the weights.
So the network tries to minimize both the error and the size of its weights.
Right. It discourages large weights. The math involves adding a term to the matrix inversion, like xx plus or 1, 1, instead of just xx. This makes the algorithm sort of perceive the input as having higher variance.
What's the practical effect?
It tends to shrink the weights on features whose covariance with the output target is low. Basically, it pushes the model to rely on many features modestly, rather than relying heavily on just a few potentially noisy ones. It encourages simpler, more robust solutions. Penalizes complexity.
Like telling it, spread your bets, don't put all your faith in one input. Makes sense. Are there other ways to fight overfitting?
Definitely. Early stopping is another really common and effective technique, very intuitive.
Stopping early. Just stop training sooner.
Pretty much. You monitor the model's performance not just on the training data, but on a separate validation set data it hasn't trained on.
Okay.
Initially, error on both sets goes down. But at some point, the training error keeps dropping as the model overfits, while the validation error starts to creep back up. That's your signal.
Stop training right there before it gets worse on the unseen data.
Exactly. Halt training before a minimum of the training error has been reached. It represents a way of limiting the effective network complexity. The book notes it gives similar behavior to regularization, using a simple weight decay term. Simple, pragmatic, often works wonders.
The book also mentions hyperparameters a lot. How do they fit into making things stable?
Hyperparameters are the knobs and dials you set before training starts. They aren't learned from the data like the weights are.
Like the learning rate we talked about.
Exactly. Learning rate, number of layers, number of neurons per layer, the strength of that L2 regularization, the alpha value. Tons of them. The book mentions A and B and beta distributions as examples in Bayesian contexts, how they control certainty.
So getting these right is critical for controlling complexity and guiding the learning.
Absolutely crucial. Tuning hyperparameters is a huge part of the practical workflow. It directly impacts regularization, stability, everything. It's often more art than science, involving a lot of experimentation.
And one last piece, data preparation. Pre-processing and feature extraction. How important is cleaning up the data before it hits the network?
Hugely important, often underestimated. The book stresses the benefit of breaking down the mapping into an initial pre-processing stage, often involving feature extraction.
So not just feeding raw data in.
Right. Transforming the raw inputs into something cleaner, more informative. Like, instead of raw pixels for character recognition, maybe extract features like line thickness or curvature first. Or for speech, turn raw audio into a spectrogram.
Making the network's job easier.
Much easier.
Yeah.
Greatly improves the performance. The network gets more meaningful features to start with, less noise. It can then focus its learning power on the higher level patterns. It's about helping the model succeed by giving it better ingredients.
Okay, so we've covered the core principles, the foundations, the deep learning Bible really solidified. Architectures, optimization, regularization, the bedrock.
The unified framework, yeah.
But then the book and the field push beyond that into more specialized, more powerful architectures, tackling problems that seemed impossible before.
Building on that solid foundation.
Let's talk about moving beyond static inputs, like single images to handling sequences, language, speech, time series. That needed new ideas, right?
Absolutely. That was a major hurdle for standard feed-forward networks. They treat every input independently.
Which doesn't work for sequences where order matters, like language.
Exactly. Understanding a sentence requires remembering what came before. Feed-forward nets have no memory of past inputs. They couldn't handle context, grammar, temporal dependencies in speech, music, financial data. Anything sequential.
So we needed networks with memory.
We did, which led to recurrent neural networks, RNNs, and then crucially, to LSTMs.
Oh, LSTMs, long short-term memory. You called them a game changer. The deep learning book really highlights them.
Oh, they absolutely were. The LSTM block diagram in figure 10.16 of the textbook, that's iconic. It represents a solution to a massive problem.
What was the problem with simpler RNNs before LSTMs?
They struggled desperately with long sequences. They suffered from the vanishing gradient problem, or sometimes the exploding gradient problem.
Meaning the error signals got too small or too big to learn effectively over time.
Precisely. They basically couldn't remember information for very long. Gradients would shrink to nothing or blow up, making training impossible for long-term dependencies. LSTMs were specifically designed to fix this.
How? What's their secret sauce?
Gates. Specialized gating units that control the flow of information within the LSTM cell.
Gates. Okay, unpack that. Like controlling what gets remembered.
Exactly. Think of them like smart filters. There's a sigmoidal input gate, decides how much new information gets led into the cell's memory state.
Okay.
Then, critically, there's a linear self-loop whose weight is controlled by the forget gate. This forget gate decides how much of the old memory to keep or discard. This ability to selectively forget is key to handling long sequences.
So it can hold on to relevant info from way back and ditch irrelevant stuff.
That's the idea. And finally, an output gate controls how much of the internal memory state is actually revealed or passed on to the next step.
Oh, that's intricate. A lot of internal control.
It is. These gating units control the flow of information very precisely. They have this internal recurrence, a self-loop controlled by the gates, plus the outer recurrence of the RNN. That's what lets them learn those crucial long-term dependencies.
And the book mentions deeper LSTM architectures being used successfully too.
Yes, citing Graves et al. And Pascanu et al. LSTMs didn't just solve a problem, they enabled much more complex sequential models. A massive leap forward for natural language processing, speech recognition, machine translation, #3.2, the rise of transformers and large language models.
LSTMs were huge, no doubt. But deep learning didn't stop evolving. The deep learning Bible laid the groundwork, and then came, well, even bigger things, like Google inventions like the transformer.
Right. The transformer architecture, introduced in 2017, was another quantum leap. Even though the textbook predates it, the principles it established were essential.
What did transformers do differently? How did they improve on LSTMs?
They basically threw out recurrence altogether. LSTMs process sequences, step by step. Transformers use something called self-attention.
Self-attention.
It allows the model to weigh the importance of all other words in the input sequence when processing a given word, regardless of their distance. It can look at the whole sentence or even paragraph at once.
So better handling of long-range dependencies. And maybe faster training.
Both. The lack of recurrence meant they could be parallelized much more effectively during training. This scalability was revolutionary. It directly enabled the massive models we see today.
Like BERT, you mentioned Bertology.
Exactly. BERT showed what transformer-based models could do for language understanding, predicting mask words, understanding context, nuance.
Yeah.
It kicked off a whole new era in NLP, far beyond what LSTMs could easily achieve at that scale.
But these models got huge, right? Billions, now trillions of parameters. Training them must be an astronomical challenge. How did the field handle that scaling and parallelism problem?
Staggering challenge. It required entirely new software stacks and techniques. Things like Megatron LM from NVIDIA or Mesh TensorFlow from Google. Figured out how to intelligently split transformer models across many GPUs.
Splitting the model itself, not just the data.
Yes, because even with data parallelism, where each GPU processes a batch of data, every GPU still traditionally needed a full copy of the entire model, weights, optimizer states, gradients. As models ballooned, that became impossible. You hit a memory wall.
Too big for a single GPU's memory.
Way too big. So techniques pioneered by systems like DeepSpeed from Microsoft and Fairscale from Facebook introduced concepts like Zero, the Zero Redundancy Optimizer, or FSTP, fully sharded data parallel.
Sharded, meaning broken into pieces.
Exactly. They partition or shard the model's state, the weights, gradients, optimizer states, across all the GPUs in the cluster. Each GPU only holds a slice.
So the GPUs collectively pool their memory to hold one massive model.
That's the core idea. Plus, clever tricks like offloading parts to CPU memory, or recomputing parts instead of storing them, gradient checkpointing. These engineering breakthroughs were absolutely essential for training models like GPT-3, GPT-4, PoleM, giants.
Incredible engineering, and these scaled models then enabled new training techniques, like making them more aligned. You mentioned RLHF and ChatGPT.
Right, reinforcement learning from human feedback.
Yeah.
Scaling made it possible to train these huge models, and then RLHF provided a way to fine-tune them to be more helpful and harmless.
How does RLHF work, basically?
It was inspired by earlier work on training agents based on human preferences. You have the big language model generate several responses. Humans rank them, which is best, second best, etc., based on helpfulness, safety, truthfulness.
Humans provide the quality signal.
Yes. That ranking data trains a separate reward model. This reward model learns to predict how humans would rank any response. Then you use reinforcement learning to fine-tune the original big language model, using the reward model's score as the reward signal. You're essentially training the LLM to produce outputs that the reward model thinks humans will like.
And this made models like InstructGPT, the precursor to ChatGPT, much better.
Much more aligned, yes. Less likely to produce irrelevant or harmful answers, users found them more useful. And, connecting to the bigger picture, ChatGPT, as known publicly, is essentially this kind of model, a combination of massive scale, transformer architecture, and this human feedback loop. Hashtag tag 3.3 architectural innovations for efficiency and depth.
So scale is clearly king in many ways. Bigger models, more compute, more data. But the sources also mention that just blindly making models deeper or wider isn't always the best strategy. Diminishing returns, rising costs.
Absolutely. Naive scaling hits a wall eventually. You need to be smarter about how you use your parameters and compute.
How did researchers get smarter? How do you allocate capacity in a smarter manner?
Two big ideas emerged: compound scaling and neural architecture search, or NAS.
Compound scaling, like in the efficient net models.
Exactly. EfficientNet was the prime example. Instead of just scaling one dimension, making the network deeper or wider, or using higher resolution, compound scaling involves balancing and scaling all these dimensions together using a carefully determined set of coefficients.
Finding the optimal ratio between depth, width, and resolution.
Kind of, yeah. Finding a sweet spot to get more accuracy per parameter or per FLOP. More bang for your buck.
And neural architecture search, NAS, Sounds like automating the design process.
It is. Using search algorithms, sometimes even reinforcement learning or other neural nets, to automatically discover novel, high-performing network architectures directly from the data. Models like RegNet came out of this, exploring design spaces systematically.
So letting the machine find better architectures than humans might design by hand.
That's the promise. It moves beyond human intuition and trial and error towards more principled automated design, smarter allocation of resources.
Okay, smarter architectures for training. What about making them efficient after training? For running on, say, your phone. Limited power, limited memory.
That's where quantization-aware training, QAT, comes in. Hugely important for deployment.
Quantization. Reducing the precision of the numbers.
Exactly. Models are usually trained using 32-bit floating point numbers, high precision but computationally expensive and memory hungry. Quantization reduces this, maybe down to 8-bit integers.
Which makes them much smaller and faster. But doesn't that hurt accuracy?
It can, if you just quantize naively after training. QAT avoids this by incorporating quantization in the training loop itself. The model learns during training to be robust to this lower precision.
So it knows it's going to be quantized later and adjusts accordingly.
Precisely. It simulates the effects of quantization during training. This way, you maintain much higher accuracy while still getting the benefits of efficient inference on resource-constrained devices. It bridges the gap between powerful training and practical deployment.
All right, so we've seen the foundations laid by the deep learning Bible, the advanced architectures that followed. Now we're really at the coming of age. This isn't just theory anymore, it's reshaping the world.
The real-world impact is undeniable.
But with that impact come big applications and also big questions, big challenges. Let's start with the applications. What amazing things are possible now because deep learning matured? Hashtag tag 4.1 real-world applications born from deep learning's maturity. So what does this all mean? Well, one really striking thing is AI generating lifelike voices. Almost spooky how good it is.
It is astonishingly good. The fidelity, the intonation, nearly indistinguishable from human speech. And it's being used everywhere.
Like creating audiobooks from text.
Yeah, democratizing publishing. Generating audio overlays for apps like TikTok. Editing audio without the speaker needing to re-record. Streamlining media production. Lots of upsides.
There's a dark side too, right? The potential for misuse.
Absolutely. That same tech can create deepfake audio. Making celebrities seem to say offensive things. The Emma Watson example is jarring. Or worse, scamming people. Impersonating loved ones in distress. Tricking executives into transferring money.
Like that UK energy CEO.
Exactly. $250,000 lost to an AI voice clone. It's a stark reminder. Powerful tools can be used for harm. Immense power, immense responsibility.
Definitely a double-edged sword. Okay, shifting to something hopefully more positive, individualized learning. How is AI changing education?
This could be huge. Perhaps the greatest opportunity for AI in education is individualized learning. Imagine every student having a personal tutor available 24/7, adapting to their pace.
Automating grading, answering questions, freeing up teachers.
There's that too, but going beyond automation. Creating truly interactive experiences, bringing historical figures back to life for students to converse with.
Wow.
Look at Conmigo from Khan Academy. It acts as a Socratic tutor. It doesn't give answers. It asks leading questions, nudges students towards discovery, facilitates debates, brainstorming.
Making learning more active, more personalized.
And the results seem promising. Classrooms using these tools reportedly outperformed pre-COVID standards by 20 to 40%, making quality, personalized education potentially accessible to everyone. That's transformative.
Okay, voices, education. What about getting around autonomous transportation? Huge potential benefits, but also big disruption.
Massive potential. Autonomous vehicles, EVs, ride-sharing. They promise to reduce traffic, cut fossil fuel use, improve air quality.
And the safety argument.
That's maybe the strongest driver. Moshe Vardi calls it a moral imperative. Since almost all car crashes are caused by human error, the belief is self-driving cars could eliminate maybe 90% of road deaths, millions of lives saved.
That's incredibly compelling, but the disruption?
Huge. Taxi drivers, truck drivers, bus drivers, delivery drivers, many of those jobs are likely to be largely out of luck as automation takes over. It's a massive societal shift we need to prepare for retraining, economic support, progress with real costs.
And just generally, deep learning has given us these game-changing statistical tools for making predictions.
We have to talk about AlphaGo here, don't we? The Go playing AI.
Oh, AlphaGo is iconic, a true watershed moment. Because Go is so complex, relies so much on human intuition, and AlphaGo displayed both intuition and creativity.
How did it manage that? It wasn't just brute force calculation.
No, it was smarter. It combined the intuitive power of deep learning, recognizing complex patterns, predicting win probabilities, with the logical power of GeoFAI, specifically Monte Carlo tree search, to explore future moves intelligently.
A hybrid approach.
Exactly. And it made moves humans initially thought were mistakes, but turned out to be brilliant creative strokes. It showed a level of strategic insight that really blurred the lines, made people question what machine intuition could mean. Hashtag 4.2, the persistent quest for general intelligence, AGI.
AlphaGo's intuition, these increasingly capable systems, it all feeds into the bigger quest for AGI, artificial general intelligence. Is AGI like a switch? One day it's narrow AI, the next day it's general? The sources suggest it's not really like that. We don't think AI can be separated into general and not general. It's more gradual.
A spectrum.
Exactly. The history of AI reveals a gradual increase in generality. Systems become capable across more and more tasks over time. It's an evolution, not a sudden singularity.
Okay, so if it's gradual, what's holding us back now? What are the big limitations and challenges on the road to something more general?
Well, as Daniela Rose points out, current AI systems lack the true understanding and reasoning capabilities that human intelligence possesses. Deep learning gives us amazing prediction tools, sure, but moving far beyond its training data to genuinely think or understand, to generate truly new knowledge, that's still a huge gap.
The core debate seems to be, can we get there just by scaling up current methods? More data, bigger networks?
That's the multi-billion-dollar question, isn't it? Will reasoning just emerge mysteriously from scale? Or is general AI possible by training a huge deep network with gradient descent alone? Critics argue we need more symbolic reasoning, common sense, different architectures entirely.
So scale versus needing fundamentally new ideas.
It's the central tension. Will scaling be enough, or do we need a different kind of intelligence architecture?
And speaking of scale, the role of compute itself seems central to one prominent viewpoint, Ilya Sutskever's idea.
Right, Sutskever's belief that compute was king. His intuition, backed by a lot of AI history, is that if you could scale compute power up to human brain scale, AGI might just emerge.
Intelligence as an emergent property of massive computation.
That's the hypothesis.
Yeah.
That sheer processing power combined with enough data and the right learning algorithms could be sufficient. It's a big bet driving a lot of the investment in massive AI infrastructure. Hashtag tagged 4.3 ethical boundaries and societal risks.
Okay, so potential is immense. The quest for AGI is ongoing, but this coming of age forces us to confront serious ethical quandaries and societal risks. Let's unpack the big one first. Bias in AI systems. Where does it come from?
Overwhelmingly, bias often originates from biased data. It's garbage in, garbage out, but on a societal scale.
The AI learns the biases present in the data it's trained on.
Exactly. If historical data reflects societal prejudice in hiring, loan applications, policing the AI learns those patterns and reproduces them, sometimes even amplifies them.
So resume screeners might learn gender bias, facial recognition might work worse for certain groups?
All well-documented examples. Hiring, criminal justice, healthcare, bias creeps in because the data reflects an unequal world. The AI is a mirror to our own societal flaws.
So what's the fix? How do we address this baked-in bias?
It's tough. Solutions need to be multi-pronged. Fei-Fei Lai suggests diversifying the workforce in AI, bringing different perspectives to development, plus technical methods, auditing data, developing debiasing algorithms, fairness-aware models.
But can AI ever be perfectly bias-free?
Probably not. As one source notes, maybe that's the wrong measuring stick. Instead, we should measure its risk relative to the bias that is already involved in subjective processes like human decision-making. Can we make AI fairer than the solid systems it replaces? That might be a more achievable goal.
Okay, beyond bias, there's the hype problem. AI snake oil. How does that connect to deep learning success?
Well, the real breakthroughs fuel the hype. But we also tend to anthropomorphize AI, right?
Yeah.
We treat it like it has intentions, understanding, leading to misplaced trust.
Thinking it's smarter or more capable than it really is.
Yeah. And understanding how myths about AI are produced can help us build up resistance to snake oil, recognizing that sometimes it's photomation, humans still doing work behind the scenes. And Ted James' point is interesting, too.
Fears about technology or fears about capitalism.
Right. That maybe our anxiety isn't about AI itself, but how AI would be used by employers and companies to reduce workers' power and agency. The economic context matters hugely.
That's a powerful lens. It raises the stakes for things like malicious use and the truly terrifying idea of flash wars.
These are incredibly serious risks. We talked about AI voice scams.
Yeah.
But think bigger. AI-developed weapons, maybe speeding up WMD creation, or worse, AI-controlled weapons, lethal autonomous weapons, LAWDAs.
Robots making kill decisions without humans.
They've reportedly been used since 2020 in Libya. They lower the threshold for conflict. And the nightmare scenario is a flash war. Autonomous AI agents reacting to each other, escalating uncontrollably, maybe involving WMDs, faster than humans can intervene.
Triggered by misinterpretation, hallucination, spiraling out of control.
Exactly. An impossible to recover from scenario. It highlights the desperate need for international agreements and controls on military AI. Urgently.
And beneath all this, there's the sheer resource intensity, the environmental cost of training these huge models.
It's massive. Potentially, AI computing globally could use more energy than all of India. That's staggering. Yet, there's often corporate obfuscation of that impact.
Companies aren't transparent about the footprint.
Often not. They push narratives about future efficiency or AI solving climate change, while the current costs are enormous and hidden. We need more transparency and accountability there.
And finally, all this investment, all this power, it seems to be concentrating. An oligopoly of power.
The data is pretty stark. A huge shift towards large companies dominate ownership of AI models. From 11% in 2010 to 96% in 2021.
96%. Wow.
Fueled by massive private investment, $340 billion in 2021 alone, dwarfing government spending. This means a handful of tech giants control the most powerful models, the data, the talent.
They set the agenda, decide the direction of AI.
Increasingly, yes. It raises huge questions about who benefits, who controls this transformative technology, and whether its development aligns with broader human interests or just corporate ones. Power is concentrating rapidly. #tag outro.
Wow. Okay, so we've gone from McCulloch and Pitt's abstract neurons through the AI winter, the rise of MLPs, the breakthroughs in LSTMs and transformers, all the way to today's incredible applications and these, well, frankly, daunting challenges.
It's been quite the journey, hasn't it? From theory to world-changing reality.
And we've seen how deep learning matured, touching everything from voice synthesis and personalized education to autonomous driving and the very nature of strategic games like Go, but also bringing up bias, misuse, resource costs, power concentration.
Yeah, the full spectrum.
It really feels like the coming of age brought both incredible capabilities and profound responsibilities.
And what's truly fascinating here, thinking back to the Deep Learning Bible, is how pivotal that book was in enabling all this.
By pulling it all together.
Exactly. By consolidating all those scattered threads, the math, the algorithms, the architectures, into one coherent, accessible framework. It provided the intellectual scaffolding. It gave everyone a common language, a solid foundation to build on.
Made the field understandable, actionable, allowed that explosion of growth.
It really did mark that transformation. From niche research to the central paradigm of AI, its legacy is immense.
So thinking forward, as these AI systems keep getting more capable, more general, where do we draw the line? Between tools and partners, between collaborators and, well, something else.
That's the million-dollar question, isn't it?
And what new Bibles will get written as AI itself continues to learn and evolve? Will we even be the main authors next time?
A slightly chilling thought, maybe.
And just how much more compute, how much more scale do we need before that thing we currently call machine intuition becomes fundamentally indistinguishable from our own? Are we just a matter of scale away?
Deep questions to ponder.
We definitely encourage you to reflect on all this. Keep exploring this rapidly changing world of AI. There's certainly a lot to think about.